Hello and welcome back to Dr. Logic awkwardly does logic in her bedroom. Are you ready to put some variables into buckets? In this video, I'm just going to go through a simple example that illustrates the definition that I gave in the previous video. So actually, if I bring my whiteboard up, I still have the definition, but I'm going to get rid of it right away because we're going to need all the space. Now, the way the definition was expressed, we start with the atomic formulas and we build up to the more complex. But you can also actually start at the most complex and kind of wind your way down to the atomic ones in order to calculate what the sets are going to be. So that's what we're going to do just because it's a little bit more interesting. So here is our example. Let phi be the formula. For all x, there is a y, r, x, y, z, and exists x, r, x, y, y. Now, the first thing to remember is that when you have a conjunction, the variables in the entire conjunction are just the union of the variables in each conjunct. So what we're going to do is we're going to look at each of these separately, and then we can put everything back together. So what are the variables in for all x exists y, r, x, y, z? Well, by our definition, this is going to be all of the variables in exists y, r, x, y, z, along with x. But this set is going to be the same as, as all of the variables in r, x, y, z, along with, well, x, because we need to have that, but also y. Now here we have an atomic formula, and the variables in this atomic formula are just going to be the variables of each of the terms in the atomic formulas. So x is our first term, y is our second term, and z is our third term. Then we're still going to have x and y. And if you recall back from 2 videos ago, you calculate the variables that occur in a variable just by taking that variable. So we have x and y and z and x and y. And if you put all of these into a bucket, look at this. It's a bucket. Let's put a handle on our bucket. Oh, I tried to make it a different color, but I failed to grab the color. Anyway, there is our bucket, and into it we will put x from here. We will put y. We will put z. And well, you know, I've already put x in there and I've already put y in there. So putting them in there doesn't change anything. They are already in there. You can't put something in again that's already in there. So this is all of the variables in the first conjunct. In the second conjunct, if we want to know what are the variables in r exists x, r, x, y, y, well, this is going to be all of the variables in r, x, y, y, along with x. And all of the variables in r, x, y, y, this is another atomic proposition, so it's going to be the variables in each of the terms. So that's the variables in x, the variables in y, and the variables in y, along with x. Well, this just is the set containing x. This is the set containing y. This already is the same thing, so I'm just going to kind of ignore this because I've already got y. And then again, if we want to look at another little bucket, let's get some nice staves on there, maybe a metal band to help reinforce it. There. This time, I'm going to get a proper blue handle. And now we put in x, and we put in y, and well, we don't put in x because x is already in there. Now, in order to get the variables for this entire formula, so this entire thing, well, we would just take everything from this bucket and pour it into this bucket, and everything into this bucket and pour it into this bucket. So this one contains just X, Y, and Z, because again, once I put X in, putting it in again, I don't get like another copy of X, I just get X. So that's for calculating the variables. But let's look at the bound variables and the free variables. So the bound variables of for all x exists y are x, y, z is going to be everything that was bound. Everything that is bound in exists y are x, y, z, along with x, because x has become bound. The free variables of for all x exists y are x, y, z is going to be all of the variables that were free in exists y are x, y, z. I'm running out of space. Subtracting x from it. So now we want to know, well, what are the bound variables in exists y are x, y, z? Well, these are going to be whichever ones were bound in r, x, y, z along with y. So those two are the same thing. And the free variables of exists y are x, y, z is just going to be the free variables of r, x, y, z, subtracting from it y. So these two, let's do a bit of this one and this one are the same set. We're beginning to run out of space just a little bit, but I can still get in what I want to do. So the bound variables of an atomic formula R, X, Y, Z just are the empty set. There are no bound variables. So this means that the bound variables of the entire formula are going to be Y and X. Or at least, sorry, not the entire formula, of this conjunct. Over here, again, the free variables of R, X, Y, yes, sorry, I got confused for a moment, but I shouldn't have. This just is going to be the variables in X and in Y and in Z. So in this case, we have X, Y, and Z, except we take away Y and we take away X. So the free variables are going to be, I'm not going to write the formula out because I'm running out of space. It's just going to be Z, whereas over here, these are bound. Now, we don't have the space on the whiteboard to go through it, but what you would see if you calculated that for this conjunct, here we have that the free variable is Y and the bound variable is X. So if we put these two together, if we take all of the things that are bound, then we get X and Y plus Y. X and Y plus X. If we take all of the free variables, you've got Z and you've got Y, and it turns out that in this formula, Y is free in one conjunct and bound in the other. So this is why it's important to pay attention to occurrences of variables as opposed to just assuming that if a variable is free, then it is always free. It can sometimes be free and sometimes be bound in one and the same formula. And that's because of the scope of the quantifiers. The scope of this quantifier here only extends as far as this atomic formula. It then basically gets stopped by the conjunction and doesn't reach over onto this side. So I hope this example was useful. And honestly, the best way to kind of ensure that you understand how to identify free variables and bound variables is to just write down some formulas and follow the calculation in the definition. If you have also learned how to use the predicate parse trees, then that's another easy way to help you identify whether something is bound or not. So if you have a variable that has, if you kind of trace its branch all the way back to the root, and there's a matching quantifier in that branch, then the occurrence of the variable will be bound. If there isn't, it's free. So that's another way that you can use to identify and distinguish between free and bound variables. In the next video, I will talk about why all of this matters. And it matters quite a bit because this is what allows us to actually generate the expressive power of the quantifiers. We need to be able to identify when we have free variables and when we don't, because that will be what allows us to do substitution. So I hope you will join me then. Until then, take care and cheers.